It is recording. Okay, good. All right, so if you go on Blackboard under Content, you're going to see a number of different files here. This is going to become available at 11 o'clock. This is Exam 1 take-home portion. You click on it, and it'll automatically download for you. Right? Someday it might. This exam's really long. It's going to take you days. It's just taking a long time to download for some reason.
I've had that same problem. I think the content delivery network for Blackboard is not that great.
That's correct. It's awful. Okay, so here it is. It'll be made available at 11 o'clock, and it's due on this desk at 9:30, because once 9:30 hits, that's when the Aiden's class portion. If I don't have it by then, you better have a very good reason, right? So no exceptions unless there's a very good one. You have to work on this by yourself. Okay, so this is preparation for the exam. You may not ask any other student or any other professor, just me or the TA, Mr. Humphrey. You may use your class and homework submissions. You can use the textbook. You may use the list of TGO and example questions on Blackboard, the professional development files, and the resume video, which I'll show you that is in a moment. And you may also use the videos I posted from lecture. You may not use any other online source. Very simple. So, on your cover page, on the front of the page, you need to write this statement. I pledge my honor, I have not cheated, nor will I cheat on this exam. You have to write that out, and then you have to write the pledge, and then you have to sign your name. So then the next part is, I have found a job description on AMD's website that when you complete this class, you'll actually be qualified for. And so the whole point of going through the video and building up the resume is to be able to go through here and see what it is that you're learning in this course and how you can translate that properly towards getting a job. So the whole point of my exams, the way that I do them, is we're simulating a job application process. You find this job for a design engineer at AMD. And so the job is to deploy and integrate on-chip, debug, and performance monitoring circuits. So key responsibilities, you'll develop hardware features related to performance monitoring. Performance, sound familiar? It's a term you learned here. And at-speed debug tracing. Coordinate Verilog RTL feature delivery, which you'll learn when we get to the cadence at the end of class. And SoC is system on chip, test benches, and hardware emulators. Ensure that all design teams have documents for system on chip bring up activities. Requirements: Bachelor of Science in Electrical Engineering, Computer Engineering, that's you. Minimum 3-month experience in computer architecture, microarchitecture, and or VLSI design. Where do you think you're getting your 3 months of computer architecture experience? Here. So by taking this class and doing the projects, you have met the qualification for this job. And in fact, even on job description, good understanding of computer organization / architecture. So that's actually on the job description. So that's why question number 1 is going to be define and differentiate between computer architecture and computer organization. It's a job requirement. It's a very common job question. I'm trying my best to put you all in the best possible position to succeed. So then you go through excellent knowledge of C and Linux design environments, MIPS to C coding. So we're going over that starting today. Problem solving, strong written and verbal communication skills. So part of that's why I'm having you guys learn the professional emails, right? So that way you stick out when you actually submit your cover sheet. Demonstrate ability to build strong influential relationships, on-time project delivery, so you'll be able to claim that after completing projects in this class and other classes, and so forth. So, part 1, it's worth 25 of the, I think that's out of 300 total. I've got the sample resume under content and professional development, right? So you go to content, you go to professional development, and here I have sample resume for students, sample cover letter, power verbs for effective resume, and take-home exam guide and resume writing video. I posted the video here instead of Blackboard because I want you to have that. I don't want students at Mississippi State to have that, or Auburn. I want you all to have the advantage over them. That's why I posted it here and not on YouTube. So you click on sample resume for students and it should download a Word document. And then after a moment, it should open it for you. We're scanning it for security. It's safe. There you go. And so what you're going to see, this resume format was developed by Intel to help veterans transition back from the military. So this is one that I had wrote up a few years ago. The common question I think many of you are thinking is, what if I don't have that much experience? That's why we're doing this assignment, to help you kind of convey other things you've done into credible resume items. So you have this opening statement here, which you describe who you are and what your skills are and why somebody should hire you. That's why, you want this, right? It's because you want to get a job. So design engineer, this was a specific resume that I had used that actually got a job offer from Intel up in Bremerton, Washington. So physical design engineer. So these are terms that are from the job solicitation. I was able to do those things, but you want to be able to make sure that the person who's looking at your resume can look at the job description and see what it is that you're doing. Something that we rarely tell students, and I think should be told to students all the time. The person who's reviewing your resume is more than likely not qualified to do that job. They are a human resources person, and it's their job to make sure that the company has crossed all their T's and dotted all their I's. So when they get audited, they have to say, why did I hire you, right? Why did I hire Alexis? So if I hire Alexis and then she doesn't have all these things on her resume, how can I justify that I should hire her, right? So you go through, and I want to be clear, I'm not saying lie, and I'm not saying embellish. You have to use the terminology that they're using to describe your qualifications, just so that it makes it easier, right? So when I was applying for jobs, I ended up having 70 slightly different resumes, but I got a lot of callbacks that people who with my level of qualifications typically didn't do, because I made it easier for those people to say, this is why he's qualified for the position. So that's take-home exam 1. So, the resume. So innovative design engineer, at this point, have been 4 years of experience in research in physical design, implementation and verification, and design automation. So this is a design automation position, going through synthesis. With strong analytical and problem-solving skills. Strong technical background and synthesis verification. You see, these are the terms that they were looking for in the position that they actually stated in the job solicitation. So they can go, yep, yep, yep. And then highly motivated and independent with leadership experience. Okay? So able to independently produce research, lead teams on projects, and use verbal and written communication skills to present research. So there's another sheet on there that says power verbs. You want to use active voice, not passive voice. You don't want to say, well, I'd like to do that, or I think we can do that. Be confident in yourself. Sometimes it can be really, writing these things out, you have to be self-reflective, and you don't want to be too braggadocio. But at the same time, you've developed those skills, right? You went through elementary, middle school, and high school. You've made it through this so far through 385. You've written TGOs to the point your hand shakes sometimes. You've earned a lot of qualifications already. Give yourself the credit you deserve. I have a story with my TA, George Humphrey. In fact, I might have. So this is his resume that we developed, and he allows us to do that. So he's got an engineering position. So he actually, product engineering intern associate. That's the name of the job solicitation. So he filled out that way. So he's talking about strong technical background and verification. So these are his specific skills. Highly motivated, independent with military leadership experience. It's said on their website that people with military backgrounds get a couple extra points. So we made a point right off early. George was in the Army National Guard. He's been to Afghanistan. So his previous resume, he had been working to go through school at one of the vet locations in town. He's taking care of dogs and shaving dogs and cleaning up after them while doing this. And so the first thing he had in his resume initially, trying to get a job in a technical company, was I clean up after dogs. And so I did the high school students. I showed them the first resume, and they're like, "Would you hire this person?" I'm like, no, he doesn't talk about that. Then I worked with him on this. We got all of his different technical skills. You're going to pick up Verilog and Verilog VLSI CAD tools. That's Cadence. Some of you have dealt with MATLAB already, right? So put MATLAB. Synthesis RTL coding. We're going to start doing that in this section. Xilinx ISE, you'll do that in 386, and so on and so forth. And then we actually found his rate. We did all this work from what he did as an IT individual in the Army. So then relevant professional experience, that's what he's been doing his research with me. You want to state the dates that you did it, where the location in terms of both the company name or the university name and where it went. You have one brief sentence where you kind of describe an overview of what it is you did, and you want to say achievement highlights. And so the achievement highlights are projects you worked on, things that you did, job responsibilities that tell me why it is that I should hire you, right? So at some point, you want to describe your relevant professional experience. Now, this doesn't have to be in this order. Let's say you don't really have that much relevant professional experience, but you've done a lot of school projects. What your sales point is your schoolwork. So in that case, what you want to do is you want to have your schoolwork first. So that way, the people who you want to have it in the order, so that way the people who, by the time they've gotten down to that first page, they've read the stuff that makes them want to hire you, right? There's no one right way to do this, but this is a really good format. See how it's clean? It's easy to see the bullet points. In this case, he's an IT specialist in the Army National Guard, responsible for maintaining, processing, and troubleshooting military computer systems and operations. Achievement highlights: supervise, install, operate, and perform unit-level maintenance. So see this? Supervision, installing, performing. And then he describes what he did: the unit-level maintenance on multifunctional user information. Construct, edit, and test computer programs. So there's a lot that demonstrates that you're doing testing. So he's making sure that the power verbs that he's using: troubleshoot automation equipment, design automation, right? And then laboratory assistance, he's talking about some of the things he did for Dr. Hildebrandt. And then gets into his education, talks about his, he's obtained a Bachelor of Science. GPA versus major GPA. Want to figure out what those are. This is the reason why you do that. So in this case, it's common that people coming back from the military sometimes will have issues transitioning into society. George had issues with that initially, and then when he got into the point where he started clicking for him, his straight A's, which is why his major GPA is so much higher than his normal GPA. So everybody has a different story as to why certain grades are better than others, right? You want to tell your story, and if you're improving over the course of your academic career, you want to show people why it is that they're getting the best of what you've done. Does that make sense? So that's something that it's all about selling yourself. So here, projects and teaching assistantship. So this is where you get all of your projects in. Okay? This is where you want to describe what you've done in your classes. So you describe how much time you've done it for each class, what the project was, and you want to tie that into what it is that you've been doing in the class, right? So advanced digital systems, member of a 3-person team that designed, simulated, synthesized RTL for a pipeline 32-bit net data path in VHDL. And so you look at the description, you see there's VHDL. Sorry, let me go back to the other place here. So you go back here, you see there's VHDL and Verilog, right? So Verilog's becoming more common in industry. This is why I've switched it for you guys into Verilog. But Verilog and VHDL are deep understanding of digital electronics and gigahertz class data buses. So that's why we're starting to do Amdahl's law and performance questions in that way. So you got, what's 3 gigahertz versus 2 gigahertz? How do you switch around different things? All right, so you build up the resume. And you actually act like you're going to apply for this job. So you're building up the resume. And to give you a motivation, is this a job that you're qualified for? Once you complete this course and do everything, you're qualified for a $101,000 job. So just a little motivator here, in case you're wondering why I'm having you do this. Trying to get you paid. Step 2. So both of these are due this coming Tuesday. So you do the resume, and then preparing for the interview. So congratulations, your resume impressed the design engineering group at AMD and you've received the interview offer. So now you have to sit down and review what it is that you know, right? It's just like you're reviewing for an exam. So in this case, I've gone over the basic concepts that you'll need to know. You go through your notes, review these, figure out computer architecture, computer organization, main goal of MIPS, basic philosophy of MIPS, define and differentiate between clock cycle time, clock rate, and CPI. So if you know those, right, you can then go forth and solve all these other problems. State clearly Amdahl's law, attribute format, pseudocode for algorithms. So now you're going through and you're quantifying your actual studying. So first part, we have job description, you build the resume for it, and then you pretend like, well, not pretend, we're saying that you've been offered an interview. So now in the course of your studying for this test, it's like you're preparing for a job interview. And then the in-class portion is going to be what we reviewed last time, where you're actually going to be performing an interview. Does that make sense? So that's the way you'll be doing that. And so what will happen is when I give back your exams, I will provide you feedback on your resume. So that way when you do resume for exam 2, you just use that, get my feedback, tailor it to that next job description. And then by the time you're done with the class, you've had 3 opportunities to get feedback and improve a resume. So then in class on Tuesday will be the in-class portion of the exam. So I have posted a 30-minute video. I've already told you about the video. It's on professional development. You can go through here, and I go into a lot more detail. Yes, Kate?
For the take-home, so we're turning in a resume, and then those questions are written down.
Yeah, yes. So in class, you asked me the question in the middle of me answering it. Let's do on Tuesday. Resume. The 15 questions. Right? So parts 1 and 2 are due in class on Tuesday. The Tuesday will be the 75-minute exam. What we cover today in class from section 4, those topical guide objectives are due on Thursday. Because those have nothing to do with the exam. I don't want you wasting your time on that. So you turn those in a week from today. So let me ask you really quickly. When is the resume due? Tuesday. When is the take-home portion with the 15 problems due? Tuesday. When is the in-class portion of the exam? Tuesday. When are the TGAs that are covered today start due? Thursday. Awesome. Does anybody have any questions about it? Yes.
Just about the resume. So when you said put your relevant professional experience, so if you have experience that's not relevant to the job, is it important to list that at all, or just completely leave that off?
It depends. So I kind of cover it more in the video. There's a half-hour video where I go into a lot more detail on that specific point. But the short version, so in your case, it really depends on how much experience you have. So I started work when I was 18. I don't want to list that I started out doing landscaping for a year and a half when my next job was nuclear reactor operator in the Navy, right? So when you have enough experience like that, you want to list your relevant professional experience. But if you don't have, if all you have is jobs that, you've worked at McDonald's, for example, or you're working the late shift at Taco Bell, you do want to indicate that you've been gainfully employed so that way somebody can verify your experience. And sometimes there's things that, if you're working the late shift at Taco Bell, there's responsibilities that you may not have. You have to maybe you have to supervise other people who are cooking. So that supervision is something that's a part of the position. You want to list anything that can sell you something in the job description that indicates that you could have already done something that's a part of that job. Does that make? I know it's not a concrete answer. There's no one right answer to these things. I do want to get started on the lecture. What I would recommend you guys do, watch the video, and if you have any more detailed questions, I will be at a conference today and tomorrow, but over the weekend I will be answering questions all that time. The one thing I can't do, just because I wouldn't be fair, because I don't have the time to do it for everybody before the test, is please don't send me your resume first and ask me to edit it. I can't do all of that for you. There's no time to provide that service for everybody. So, are there any other questions? Awesome. All right. Okay, MIPS to C coding. So at this point, we've kind of gone over computing performance. We've gone over what a register is. We've gone over what cache memory is. We've gone all the different types of memory addressing. We've gone over arithmetic logic unit, where we went over addition, subtraction. Then we use addition and subtraction to perform sign multiplication, restoring and non-restoring division. And then we also learned about the IEEE 754 format, where we can do basically scientific notation in binary. So now we're going to start combining this into what happens when you write code and you need to execute it out in a data path. So we're going to look at this, and then the last step is, once we have a general idea how the code flows and how we can put all the pieces together. You've learned about the pieces, and in section 5 we're actually going to build the data path. So we've kind of already covered the concept of registers here. We've talked about register transfer instructions, and so the whole idea of that is that you have 2 registers of R-type instruction from some operation within the ALU. Remember, our ALU has 2 inputs and 1 output, and then you store that result in a 3rd register. And so we have RS and RT. So basically what I'm talking about here is, you remember I gave you an example of how you add 3 numbers? So you have 3 register values. You have to add 2 register values and store them in a temporary register value, and then add the temporary register in the 3rd value and store that into the register. So F equals A plus B plus C is temporary is A plus B, and then temporary plus C is F. And so we'll go over all that. So we've also talked about single write SRAM and DRAM. And so here is example 4.1. And so we have a very basic C code line. A equals B plus C plus D. And so before you go into what I do want to show you that's also going to be helpful for you as you study for this, when you go under content and reference files, the thing that you're going to really want to be aware of is this thing called the MIPS green sheet. If you have, for those of you with the textbook, it's that green sheet on the front page that has all of the instruction types and all the registers. So these are all of the instructions that can be done by the MIPS data path. If you recall, these are the instruction formats: R-type, I-type, and J-type. So you've got opcode 30 bits 31 to 26. 25 to 21, those are 5 bits, 5 bits, and 5 bits for RS, RT, and RD. Shift amount and function, and then opcode and jump for 26. So here, what we're doing is we have add. And so the operation in Verilog, register RS plus register RT is then put into register RD. And so we can look at this and we can actually put together the entire instruction. We have an opcode. This opcode value here is 0, and the function is 20 hex. That means that the first 6 bits are all zeros, right? The next 5 bits are RS. That's the first value we're adding. Next value is RT. That's 5 bits. And remember, if you registered addressing, where we have 5 bits and it's converted to a 5 to 32-bit decoder, and it selects the specific register that I want. That's what's going on here. This is memory. So I have a register address. I have a register address. I have function code. So shift amount 0 because we have RD, which is our destination register. Shift amount is 0 because we're not shifting, and then 20 hex is just 10. Like that, right? Because it's the last 6 bits. And the reason we can claim that is because down here, that's the function here. So it's bits 5 through 0. And so 20 hex is basically their way of converting from hexadecimal to 6 bits in binary. So 29 hex is just 101001, right? 2B hex, that's 11. So 10, 10, 11. So that's B hex, right? And so the whole idea here is you're actually using these to do this. So here's subtraction. RS minus RT performed in the ALU. It's 22 hex, right? So 20 hex is 100000. 22 hex is 100010. And if you recall from when we were talking about add and subtract, we just used the difference in function value to use as the input for a carry-in, as well as the XOR. Remember how we were talking about that? That's where design of the computer architecture can then be used to manipulate the computer organization. The computer organization is how you design the adder subtractor. And computer architecture is how you manipulate the function values to be able to do that. Does that make sense? So that's why it's important to know the difference between architecture and organization. So in this case, we'll go back to 4.1. So now what we're doing here is we have, these are the MIPS instruction types. So it can be a little confusing here. So I just want to go over this with you real quick. I know you all want to write this down because that's what the homework is. But here's how it works. And you can go over the MIPS screen sheets to make it clear. So add. And so the destination register is always first in R-type instructions. So it's going to be temporary because we take two values and we're storing in a temporary register. And so in this case, in the problem, A is in S0, B is in S1, C is in S2, and D is in S6. So I just want to ask this question to reiterate the point. Why can't I do S1 plus S2 goes into S6? Oh, I'll solve the problem, then I'll ask the question again. So it goes in a temporary register, S1 plus 2 goes into a temporary register, and then T0 plus S6 is D, right? A equals B plus C plus D. So temporary plus D now goes into A, right? So this gives us A equals, and then B and C went into a temporary register plus D. So the question is, why can't I do this? Why can't I do add S0, S1, and S2, where I'm adding B and C and putting it into A, and then S0 plus S6, goes into S0. Why is that wrong? Sorry. Go ahead, try it. You probably said the right thing. Go ahead. Have confidence in yourself. The worst you can be is wrong on your guess, and no one's going to care. Seriously, give it a try. I can wait you out. Does anybody else have a guess? Yes.
Is it because you're actually permanently changing the value there?
Correct. Exactly right. The coder did not write. That would be A equals B plus C, and then A equals A plus D. That is not equal to this. You have to write you have to put what the coder gives you. And also, when we get into this in section 6 about parallelism, and you're putting multiple elements into different processors, and you separate them out, if you have the wrong value of A, somebody might need the current value of A, and then actually get a wrong value. So A, according to the coder, is never B plus C, so it should never be B plus C in the data path. Does that make sense? So that's why that's wrong. That's why we have to use this temporary register to store the value of B plus C, and then B. This is B plus C, and then this is plus D, and that's stored in the value of A. Is that, Alexis? Is that what you were going to guess? Should have done it. Should have done it. You were right. All right. So this is the next part. So how do we actually convert this into binary? So remember, you write some code in C or Java or C++ or whatever your programming language is, and then it puts it in an assembly language. That assembly language was the add T0, S1, S2, right? That's assembly language. So you have to put it in assembly language and then MIPS machine code. So this is the first part. We've put this in assembly language, so that is proper assembly language. So then what we're going to do is, using our MIPS screen sheet, we're actually going to convert it. So the first instruction is add T0, S1, and S2, right? So this is where knowing the MIPS, reviewing the MIPS screen sheet becomes useful. So in the case of the MIPS screen sheet, we now want to look there and see which values correlate to which register. So we have these register names here, and this will eventually be a topical guide objective. We look here, and then we can correlate these numbers to the register values. So in this case, the saved temporaries are S0 through S7. So it's 16 is S0, and you add it from there. So we're doing S1 and S2. So that means we need register 17 and register 18. And then we're storing it in temporary register 0. So T0 through T7 are 8 through 15, and then T8 through T9 are 24 and 25. Now, I can promise you that on any homework assignment or quiz or exam, there will never be any kind of problem where you will be required to have more than 8 temporary registers. In fact, I don't think I've ever given one with more than 3. So you'll never need 24 and 25. And so what that does is we can now look at this and say, how do we convert these values? So we know the opcode was 6 bits of 0, right, for addition. So opcode is 0, 0, 0, 0, 0. Shift amount's 5 zeros because we're not shifting anything. And then we just look, these are the values that correlate from the green sheet like we just did. So S0 is 16, S1 is 17, S2 is 18, S3 is 19, and S6 is 22. And then T0 is 8. So then what we do is we have opcode is 0, then RS, this is where it gets confusing because in the assembly language, these are the two that you add. In the machine language, the way they've designed it, and when we see the data path, this will make more sense as to why this is done this way. They laid it out physically here, such that these two are next to each other. And then the destination register is here. So see, this is 17. So that's 17, and that correlates to S1. This one's 18, and that correlates to S2. And then the destination register is 8, which is T0. Shift amount 0, and function, if you recall from the, is 20 hex, right? So you have 20 hex, and it's there. And then the same thing for the next problem. So these are the actual machine codes. And then the same thing, it's addition. So then what we're doing is we're adding T0 plus S6. So that's 16 plus 6 is 22. And then we're storing them in register 16 because that's S0, right? Shift amount 0, and function is 20 hex or 100000. Does that make sense? So now what we have done is based on our knowledge of the computer architecture and the computer organization, we have now converted some basic C code into assembly language, which we've defined on the MIPS screen sheet, and then the assembly language to actual machine code. So this is how you can represent A equals B plus C plus D in 2 32-bit instructions. Okay, does anybody have any questions about that? So I want to go over another C code example. So here, we're adding parentheses. So you all remember back in school how order of operations is important? So order of operations is important here. In this case, because the coder, for whatever reason, has put in parentheses, we can't go T0 equals G plus H, and then T1 would be G plus H minus I. Yes? Well, okay. So this is F plus G minus I plus J. That's different than G plus H minus I plus J. That's different. So you have to do order of operations. So in this case, you're going to add, and we're going to add, and then we subtract those two values. So the best way to do it is to just store it in both of them in a temporary register. And then subtract the temporary registers and store that in registers. So the problem states, translate the following C code into MIPS register transfer language, then the MIPS assembly language, then the MIPS machine code. Assume G has already been loaded into S0, H into S1, I into S2, J into S3, and F is S4. And the reason why I phrase the question this way is because MIPS is a compiler-driven encoding of the micro engine. So when it's actually executing the code, the compiler has already allocated which registers go where. And so in this case, what we're going to do is first we're going to add G plus H. So it's going to be add. We're going to create a temporary register, T1, and we're going to add G plus H. G is S0 and H is S1. So that's S0 and S1. Next, we're going to add I plus J. So we're going to create, we can just say this is T0. It's not, you don't have to, if T1 and T2 or T0 and T1, they're both correct answers. I is S2 and J is S3, so you have S2 and S3. And then last, we want to do a subtraction where we're going to put the value of F, which is S4, and then T0 and T1. Does that make sense? So what we've done is we've created two temporary registers, used those values, and then subtracted them and stored them back in the register that we have. And that is what has come out here. Now, on an exam, I don't expect you to write this. This is what it is in Verilog. You'll have plenty of time to do Verilog later in the course. What I want you to do is I want you to take it, put it into the assembly language, and then put it into the machine language. So then what we're going to do using the MIPS screen sheet, things that we know that the opcode for both add and subtract is 0. We know that the function for add is 20 hex, and we know that subtract is 22 hex, right? And so then we just take the register values that we know from the green sheet and lay these out. So in this case, all the opcodes are the same. All opcodes for R-type instructions are all 0. So actually, if you look at the MIPS screen sheet really quickly, I can show you that. So if you look here, if you look at anything with R-type, you'll see that the opcode is 0. And the reason it's done that way is so that way when we get to the data path, there's going to be something called the ALU controller. So you have a normal controller and the ALU controller, which takes in the input from the function and goes straight to the ALU. The control unit sends control signals to everywhere else in the data path, like the registers. Do I want to write to the registers? No? Okay. So do I want to read from the data memory or write to the data memory? Those are all different controllers. Do I want to branch? But as you can see, subtract and unsigned subtraction are both 0, 0 here. R-type is there, and they have different function values. Now, I-type instructions do have opcodes. So I-type instructions are here. So let me go back here. So in this case, the first one is add. So we add. We know that T0 is where we're going to add here. So that's T0 there. S0 and S1. S0 is 16 and S1 is 17. So you see 16 and 17 there. So those are the 5-bit values. Shift amount is 0 because we're not doing any shifting. There. And then 20 hex is the last 6 bits. 20 is 10, 0, 0, 0, 0. Same thing with the second instruction. The second instruction is that instruction, right? So 0 for the opcode. Here we're adding S2, so that's 16 plus 2 is 18. 16 plus 3 is 19, so that's S3. And then T1, which we allocated for the values of I plus J. So we're adding these two values and then storing them here. We're not shifting at all, so it's all zeros, and it's 20 hex in the function value. And finally, and I know this is kind of dry material, subtraction, opcode is 0. We're taking the value of T0 and the value of T1. We're storing the result in S4. So that's 16 plus 4 is 20. We're not shifting at all. And then this is 2 hex. 2 hex for the function value means subtraction. Does that make sense? All right, so I want to go over some quick, these are a couple of quick mistakes. I think I've already gone over this one a couple of times. Why is this wrong here? So you're having addition S1 and S2. Here, what you're doing is you're subtracting and subtracting. You forgot to put in the brackets. So students forget that you have to do order of operations on the brackets. And so what they end up doing is they do 2 subtraction operations instead of 1 addition. And here the issue is you have to do what the coder told you. So in this case, minus I minus J is technically correct in that if you take the negative through, it is it'll give you the right number, but you have to do what the coder told you. If computers were that smart, we'd already have artificial intelligence, and none of us would be here. And so here, in this case, we're just storing everything in F4. So F4 is A plus G plus H, and then we're subtracting I from F, and then J from F. And while that's also technically correct, again, that is not what the code specified. So those are a couple of common student mistakes. Actually, in my experience on this, if the student has a decent understanding and makes a mistake, it'll more than likely be one of these two. So I figure I'd say, hey, don't do that. Then you get the question right on the exam. Okay. All right, so now I want to go into I-type instructions. So here we have G equals H plus 5. So we talked about everything where register values are parts of the code. But in this case, we have an actual numeric immediate value, right? So you recall from the different types of memory addressing that there was one specific one called immediate addressing. And the immediate addressing is we actually stored a numeric value in the instruction itself. Yes, no? Please remember that on Tuesday. It's going to be on your test. So that's how we actually have to store the number 5. The compiler puts the number 5 into the instruction. So I'm going to show you how the compiler does that. So the first thing we're going to do is we're going to do an add immediate instruction. And so the add immediate instruction in the MIPS green sheet is here. Add immediate. So it's an I-type instruction, and the opcode is 8 hex. And so we have RS, we have the sign extension immediate, and then RT is where we're putting the value. And then we have to put it in 8 hex. So what we're going to do here is we lay this out, and so S1 is H, S0 is G, and F is S4. So what we're doing is we're going to take this value, we're going to create a temporary value for it, and we're actually going to have the number 5. So S1 plus 5 goes into T0. Does that make sense? And then from there, we have temporary 0. Notice I've kept the order of operations the same. S0 plus T0 using R-type is stored in S4. When we go into these type of instructions, recall that the opcode for add immediate is 8. So we put, so this is 8, 6-bit value of 8 here. S1, we're adding this one here. And then the actual, we're storing it in T0, so that's our RT, that's going to be our destination register. And then we're storing it in a 16-bit value where the last 3 bits are 101 to represent 5. So I just did ... there to save time and energy. And then here we add again, 0, S0 is S0, here this is T0. We're storing that in S4 and T0 there. And if you recall base addressing from the previous topical guide objective, we have that there. Okay, so it's 1017. Let's see. All right, so what I would like, let's see, do we have an even number of students? If we have an odd number of students, I want you guys to work in groups of 2 on this. All right, when we put up the problem on, I'm just going to put it and so we're going to have a set of instructions, and I'll put up the MIPS screen sheet as well. So I'm going to have F equals A plus B minus C plus 5. And what I want you to do is I want you to do the MIPS assembly and then MIPS machine code. And you can do this in 1, 2, you can do this in 3 instructions. So I'll give you that hint. And the reason I'm making this smaller is so that way I can put up pertinent MIPS screen sheet. Oh, actually, I'll make that way. No, I haven't. I'll just keep it that way. And so yeah, you can have this in and I'll count this as 10 points on quiz score. It's not an actual quiz because you just learned the material, but you're here, you did this, you worked it on in class, I'll count that. The part of the reason I'm doing is I can start to see everybody start to fall asleep, so maybe it's something to help you keep awake. I know this is very, very dry material. You're bored right now, bored you'd be teaching it for the 8th time. Yeah, subtracts down there. So you guys got it in your, many of you have it in your notes anyway, what subtract is anyway. So. Like we're ready to talk to each other. This is not like a. Yes. Well, let me work through it as much as you can. I'll see.
Well, I was just going to ask. These are.
Oh yeah. Okay, so that's a really good. That's actually a very good question. So let us assume that S0 equals A, S1 equals B, S2 equals C, F equals. I'm sorry. S3 equals F. Yeah. That's the test. And you're permitted to work with somebody on it. I'm not grading for accuracy, I'm grading for effort. Okay, to answer the other question I'm getting, I'm not grading for accuracy, I'm grading for effort. Make your best faith effort. Well, I'm not gonna tell you the answer unless you can try to work You can pick whatever temporary yeah. Typically, people will start with T0 and count up as they do temporary manuscripts, but the key concept I would be grading on a test is that you use the temporary register, not specifically your order. It's something else, right? It's 0 to 9 and 8 represents 0 to 7. And then you just convert from 0 to 15 into 4 bit. Or 20 to 15, right? So 15 is just 1111. The 2 0 hex for that. 0.
And then you go hex 0.
The 2 0 hex is the first 4 bits. 2 1 0. Normally 3 0 0 1 0, but because it's a 6 bit value for the function. I should make a best faith effort. I'm going to keep trying based on what you know. I'm not going to answer like exact answers. So I where do we put the shit? Yeah. So based on my yeah, that's the so we're gonna try your best based on your notes that you took to put the numbers in there. Where does S0 start and where does S0 start? I don't know, it's at the end. It's like try your best. I'll go over it again. How do you see this? You are allowed to talk to other people. I see some of you still being sheepish about it. Some of you might have caught that detail about saved registers and temporary registers that you didn't catch.
The last bit 6 feet?
Yeah, is that we did subtraction in the previous problem. Remember what those were. The difference between addition and subtraction is both of your 22 hex.
How do you use this? How do you do the 8 hex representation?
Question. How many of you do not know how to convert binary to hexadecimal. Okay. All right, so it's only a couple of you. Okay, so basically just convert the hex number to decimal and then decimal to binary. Yes?
Were the register values given a hex or a decimal?
I want the machine code. I want them eventually in binary.
I know,
No, those are always. I mean, they're 0 through 8, so it's irrelevant. 0 through 8 in both hex and decimal are the same.
okay.
This is where I'm
I want you to try to write down everything. Sometimes the best way to teach you guys is to allow you to make a mistake and then correct it.
No, then it's followed by 8. So it's followed by X0 and it's followed by
First you're at the drop.
So I've moved this down so subtract and the instruction formats are all there. I'll give you guys 3 more minutes.
I think so.
So this should be one first.
Because one of them's opcode and one is function. Yeah, if you look here, opcode slash function. So the first one's the opcode, the second one's the function.
Yeah.
Oh, this one. Okay, one more.
Oh, yeah. Yeah, because it's right. So that's all
Okay. That's RT.
All right. Do you have a pen? Please take it out. And then I want you to grade yourself, and then you're going to hand it in, all right? So this is your opportunity to be honest with yourself. So don't write it in pencil. Write it in pen. So when I hand it back to you next week, you actually have this, this is where my concept error was. So, you're getting full credit for turning it in, so there's no reason to try to do anything else silly. Okay? So, here is the problem. F equals A plus B minus C plus 5. I thought, for some reason, I thought that problem just really scared you. Plus 5? Oh. So, first thing we do is we maintain order of operations. So we do an add. No, Bowen. No, I do not permit that in my class. You can take notes. I was polite about it last time, and then now it's don't do that. I'm serious. Like, some professors will throw you out of the class and give you academic dishonesty. I'll break that habit. I'm not being funny. I'm being deadly serious. You do that in Dr. Daigle's class, he'll flip out on you. Okay. So first time I said polite, now I gotta be a little less polite. Just don't do it. So first thing we gotta do is we have to have our destination register. It's a temporary register, right? So T0, A plus B. So we said S0 and S1, right? So next instruction, we have to add the other one. So it's an add immediate. Sometimes when I'm typing them out, I just like to do the tab to keep things easy. So the destination is T1. And then we have C is S2. And then, so to add immediate, we're adding 5, right? So we just add 5. So then subtract. And then we're going to store it in F, correct? So it goes S3. Then we put it T0 and T1. So basically what we're doing here is we're taking these, A plus B is T0, C plus 5 is T1, and we store these values here, right? So now we convert it to the binary. We look at the MIPS screen sheet. We know that all our type instructions are 0, so it's 6, right? Put a little dash there for understanding. And then RS is S0. We know that save temporary start at 16, so it's just 16. S1 is 17, right? T0 starts at, the temporary start at 8, so it's, see that? Shift amount is 0. Why is the shift amount 5 bits? Exactly. You're exactly right. It's 2 to the 5 is 32 bits. So that's all you got to do is shift. And then the function for add is 20 hex. So it would normally be 0010, right? That would be 20 hex. But because it's only 6 bits, we lop those 2 bits off. Same thing for the next one, add. And then we have S2, 16. What we add 2 is 18 right there. And then T1 is 9. And here we would have 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And it's 5, so it's 1, 0, 1. And then last is subtract. It's an R-type instruction. So we're taking T0, which is 8. We're subtracting T1. And we're storing it in S3, which is 16 plus 3 is 19, so 16. And then for the last 6 bits, you just do 3. Does that make sense? Shift amount is 0 because we're not shifting. And then it's 2 hex for subtraction. So it's 1 0 0 0 1 0. So that's for the subtraction. And I'll put enter values between each of those. No. Yes. See what? I'm sorry, I can't hear your question. Yeah, these are the next 16. So this is an I-type instruction. That's this guy, right? So that's 16 bits. When you're reviewing for the exam and remember the immediate addressing, we use these 16 bits in the instruction itself to store like whole numbers. In that case, it's 5. So in this specific case, we just use the last 16 bits here because it's 6 to 5 bits. So we have 16 bits that we've already used. And then it's sign immediate, which means 0. We have to have all zeros for a positive number. So if this was -5, now here's the $1 million question. Note how there's no subtract immediate instruction. This is where compiler-driven encoding of the micro engine comes into play. There's no subtract immediate. What we do is we do add immediate. And then what we would do is we would just do so that's convert them all and then add 1. So there's no subtract immediate instruction. And the reason they do that is so that the compiler can drive it and you don't have to add overhead in your control unit. You can just have the same things done by just doing 2 stuff on them. Yeah?
The opcode for add immediate?
Yep, that's a good catch. That should be 8. That comes from here. So I'll put that back up. So the app code for add immediate is 8. For all R-type instructions, add and subtract, it's all zeros, and the difference is in this 6-bit function. We have a 5-bit shift amount because you can shift up to 32 bits because we have 32-bit architecture, so it's 2 to the 5. And then we have our 5 register dies because we have 32 total registers. I-type instruction should be an opcode, 2 RS values, an RT value, and then some sort of value here. In this case, this is subtract. So does that make sense to everybody? All right, so if everybody would pass their, make sure your name's on it, so I want to give you full credit. Plus, it's a good way to reward you when you came in on a day before, or when you're not covering anything before the exam. Right? Yeah, 13 zeros, 1 0. Yeah, I'll come back to you. Did I have everybody else's assignment? All right, do I have everybody's? No, I don't have that. Does anybody have any questions on this? So you made an attempt, so that's 10 quiz points.
You did say we have the green sheet in class.
Oh yeah. I will staple a copy of the green sheet to the exam. Any quiz you get, you'll have a copy of the green sheet. And it's also on Blackboard, so if you're reviewing anything, everything covered. That's a really good question, Dee. Everything covered today will not be on the exam. No, and part of the reason I did this is to reward you for coming, even though I told you last class that nothing that would be covered today would be on the exam. On that note, you are dismissed.